All right, good afternoon, folks. So I'll be taking this lecture for Clarice. Since I didn't prepare the lecture, I don't care if we go off the roadmap. So if you have any questions in the middle of the lecture, if you have any questions, if any side routes you want to follow, I'm happy to do that for you. So please just raise your hand and let's take it as it comes. So this lecture will be about Numpy, which is the numerical manipulation library for Python, specifically when it comes to managing large numbers of numbers. So Python has lists, and lists can contain other lists. So it is possible to store vectors and matrices as Numpy lists or list of lists. So why don't we simply use Python and represent those objects in that way? Well, who wants to venture a guess? What's that? Efficiency? Yeah, that's exactly it. So NumPy arrays or Python lists are very generic. You can take a list and you can put numbers and objects and any kind of object in there. But when you work with large collections of numbers, that's not a very efficient container. How efficient is this, or how inefficient is the Python route? Well, let's take a look. So let's just start here by start at the top. Okay, can you guys at the back see, or should I make it a bit bigger? Bigger? All right, how's that looking? You can see that? Good. All right, so let's start with a bunch of numbers. We'll start with 50,000 numbers. Let's turn that into a list. Okay, so X consists of 50,000 numbers. There's the first 5 of them. And let's see how long it takes to square those numbers. So IPython has this magic command called timeIt. It runs whatever follows the timeIt command several times, and then it tells you how long that thing took to execute. So let's say element squared for each element in X. So there we go. All right, so 25 milliseconds per loop. Hey, that's almost nothing. So can NumPy do better than that? Well, let's see. So the NumPy syntax is a little bit different. You'll see that we start by importing the NumPy library as NP. I do that so I don't have to do a lot of typing down the line. So it's just shorthand for NP. And you saw early on when Josh told you about namespaces that we prefer not to import all the functions from NumPy by doing something like from NumPy import star. Why not? Well, NumPy's also got a sum function, for example, and that sum function would then override the built-in Python. So import NumPy as NP and then access all its functions as NP dot whatever. Okay, so we'll start by making an array of our existing data. Let's call it Y. So I'm taking that list and converting it into a NumPy array. And now let's do the same operation. So we're going to square each element of the list. And the NumPy shorthand for that is just Y squared. So it's a convenience syntax that will square each element inside of Y. And when we do that, IPython runs it several times. And it says 99.6 microseconds per loop. So that is a speed up of roughly 250 times. So 25 milliseconds might not seem much, but when you do more complicated numerical procedures, then 250 times makes a big difference. So how do these numbers then get stored in your memory? Well, let's think a little bit about what Python does with a normal list. So with a normal Python list, you start off with a container, the list, And inside of the container, it just stores a number of pointers or positions in memory. And each position inside the list just points to a Python object. So if you store an integer in there, then Python will create the integer for you and will make a pointer from the list to that object. If you then decide to store a string in there, it will construct the string and point to the string from inside your list. Numpy doesn't work that way. Numpy allocates one big block of memory, and then it has a clever way of describing how that memory is viewed to the computer. So in the simplest case, imagine we just worked with bytes. Bytes, numbers that run from, let's say, integers that run between 0 and 255. Each number like that occupies a single byte in computer memory. So that would be a typical representation of how the numbers are stored. Each blue block being a byte in the computer memory. And the computer memory just runs, I mean, you might have gigabytes of memory, and as part of that memory is then given to Numpy to store this array in. So Numpy puts all the numbers in memory, and then it's got some special attributes that tells it how to look at that data in memory. It stores the address of the data. It stores the shape of your array so that you can have multi-dimensional arrays. So you can have a vector, you can have a matrix, 2-dimensional, you can have a tensor, 3-dimensional, 4, 5, 6 to 31-dimensional if you want. And then Numpy stores some information on how many bytes in memory each element contains. So that's important because it turns out that you can store various different kinds of numbers inside of a Numpy array. Like you can store, like I said, an integer that runs between 0 and 255, 1 byte. Or you can store numbers that go from 0 to 65535. That's how many bytes would that take? Maybe 4? 2 or 4? And then you can go to much larger numbers than that, occupying 8 bytes in memory. You can store floating point numbers. You can store Booleans, various different kinds of numbers you can store inside of a Numpy array. But the important thing being that Numpy arrays are homogeneous. They always store one kind of element, and they store many of those. So let's start off with a very simple array. I'll make the list containing the numbers 10, 20, 30, 40, and then I'll use np.array on those same numbers. So now I have a list and an array. The list and the array can essentially be addressed in the same way or indexed in the same way. So you can, for example, if you grab the first element from the list, you get 10, same thing for the array. You can grab the last element of the array. You can grab all the numbers starting from the second, or you can get the second from last element. So similar to what you saw with lists so far. Let's look at this quickly. So I spoke about data types. So look what happens when you construct a Numpy array from the following data. So notice that the input I give to np.array is now a nested list. It's a list containing 2 elements, each of those elements being another list with 2 elements inside, 2 integers. So let me first print out x. So there you see that creates a matrix, and that matrix has a data type of int64. So it's these massive integer numbers that I was talking about. How big can these numbers be? I think Numpy will be happy to tell us. Okay, so they can go up to 9 gazillion. Yeah, I'm not exactly sure how to pronounce that. Okay, so look what happens when I do exactly the same operation, but I now replace 1 with 1.0 in the input. Suddenly, the array stays the same. I mean, it's still a 2-dimensional matrix. But now when I look at the data type, you see that it's float64. So that means it stores floating point numbers, no longer integer numbers. So Numpy is a little bit clever about knowing what kind of numbers you're trying to store in the array. Most of the time, you can just be explicit about it. So you can do something like create an array for me and make sure the data type is floating point. And then Numpy will give you a floating point array. So if I call that thing z, then z looks like that. And z.dtype should be float32. OK, so once you've set the data type of an array, you could construct a new array and change the data type. But for that specific array, the data type is fixed. So if you try and assign values into it of a different data type, surprising behavior can occur. So here I construct a NumPy array of data type uint8 that's unsigned integer 8 bits. That's just a fancy way of saying the integers from 0 to 255. And if I try and assign minus 1.234 to the last element of that array, look what happens. Doesn't work. NumPy tries its best, but that's the closest it can come. What's that?
But it doesn't complain.
No, it doesn't complain. So let us take a look what happens if you have an array consisting of these numbers going from, yes, sir?
Will you complain if you try to assign it a non-numeric, such as a string?
Let us take a look. So you want to make that something like, yeah.
How about if you make it 5,000?
No, that should be fine. You may be able to set NumPy to catch those errors. I can't remember exactly. You can have a look at np.set if you're interested in more detail. You can see that it allows you to set a whole bunch of error conditions in case you do weird things. OK, so let's take a look. I'm going to create another one of these arrays with values that can only go between 0 and 255. And then I'm going to add 1 to that array. What do you think will happen? Yeah, what will happen to that 255?
Negative.
Yeah, it's going to go to negative, because how do you, in the computer memory, remember we have 1 byte at our disposal, and the value 255, if you convert it to binary, is equal to 1111111. And if I add another 1 to that, all these, like what happens when you add 1 to 1 in binary, becomes 0. The 1 carries 0, 0, 0, 0, 0, 0, 0. So the number flips around.
But I thought we only have positive numbers.
Yeah, you do only have positive numbers. Yeah, so it goes to 0. If you subtract 1 again, then it goes the other direction. All right, so in this case, Clarice just wanted to make you aware of the fact that while we think that computers are, they store numbers the way we think about it, they use a standard called, it's like an IEEE floating point standard that they use to represent these kinds of numbers. And the number stored in computer memory is not always what you think it is. For example, it's quite confusing working with financial calculations in floating point, because very often when you store 0.3, the computer actually stores 0.3, lots of zeros, and a 1 at the end. That's just a limitation of the way the numbers are represented. So you may notice that sometimes after many zeros, you get strange numbers at the end. So I guess how that translates to scientific computing is be aware that your results aren't infinitely accurate, but there's some limit to the precision you will get. What's that? Yes, it should. Let's see. Oh, it doesn't. except if your other number is stored in the same floating point accuracy, yeah, then it will. Yeah, you can never really compare floating point numbers with equal signs. And this holds across different programming languages. You have to check that they're close to one another. And NumPy's got special machinery for telling you how far they are apart in this floating point representation. Okay, she had some more examples. I'm going to skip over those for now. So we've now seen one way to construct NumPy arrays. We've constructed NumPy arrays by explicitly providing all the elements that we put inside. But there are many other ways of constructing NumPy arrays. For example, there's the very convenient np.zeros, which just blanks out a part of the memory for you. So there I've constructed an array. The first argument is the shape. So it's going to be a 5 by 5 array. And the data type is going to be this floating point format. You could also just write it like that.
Assume the first parameter is rows.
What's that?
Assume the first parameter is rows.
Yeah, so, okay, that's probably important. The indexing here is that, let's make it 3 by 4 just to remove the confusion there. So NumPy always indexes first along the rows, then along the columns, and then if you have further dimensions, like you get the depth and what would you call it after that? I'm not sure.
So you may have mentioned that. Do you require always to specifically put the data type?
No, you don't always have to specify data type. You could have done the following, and then it will just do floating point by default.
What's the point then of putting it if Python doesn't really care?
I think it's just to make it explicit in the code. But there's, because you could, for example, do this, and that would make sense. Yeah.
It doesn't care why.
Well, so you as a programmer might not know what the default data type is. It happens to be floating point. But, you know, like if you wanted to specify int, for example, that would be necessary because otherwise you would get a floating point array. You could also make a complex array storing complex numbers. And like we just saw, that's the default is floating point. There is a marginally faster operation that some people might recommend you use. It's called np.empty, and that just grabs a chunk of the memory and it doesn't set it to 0. I would say don't go close to, don't ever use that because I've seen too many people use it and then forget to initialize the elements afterwards. Then you just get whatever was, like in your video card buffer or whatever happened to be loaded in that memory before. An empty list?
Yeah.
So what kind of array would you like to have?
If you want to initialize array with a for loop, like you create a column every iteration,
Yeah.
you initialize something to just append it to?
Yeah. So we'll see another example of that, but she's basically asking, how do I construct an array if I want to build it up sort of in an iteration in a for loop? So the best option, if you do know the number of columns beforehand that you're going to construct, you can do something like my new array is np.zeros. Maybe each element is, let's say, number of rows, number of columns. Let's say I've got 5 rows and 10 columns. So if you know beforehand you're going to construct 10 columns, just initialize the array with 0 and then do for column in range number of columns. And then you do some very complicated calculation here. I'm just going to make it whatever, and then you can do x. Okay, and now we have to do a little bit of index magic here. So I've now generated a column that I want to assign. How do I grab a specific column from a Numpy array? Well, at first I have to tell it that I'm looking for all the rows in the array. So for that you use a colon. And then I have to tell it which column to use, and that will be col. Oops, let's make this col values. So that's roughly what you would want to do. Is this clear to everyone, what's happening here? Be happy to explain it again. What's that? Yeah, so I've constructed this empty array that's 5 rows, 10 columns. And then I said I'm going to let the variable column go 0, 1, 2, 3, 4. And then, so this is just sort of a fake way of generating the column data that I'm going to put in. Normally you'd have some crazy complicated calculation here. And then you'd say X, that's my output array. Take all the rows, but only look at column number col, and then assign the values that I just calculated. So that's one way to build up the array. The other way is to have a list and just append arrays inside of the list, and then finally do np.array on that list and just construct a new array from scratch.
Can you print it out?
Hmm?
Can you show this array?
Yeah. You're presuming my code's going to execute. That's it's kind of you. Let's do something slightly more interesting. Let's make this. Okay, give me a thumbs up if that makes 100% sense. Okay, give me this if you don't really know what's going on. Yeah, okay. All right. So I think the important thing that we must understand here is probably this. Is that where things are a little bit confusing? If so, we're good because we're going to talk about that just now. What's that? Column values? Okay. This one here? This one? So how do I construct column values? I call the np.arange function. That's the same as NumPy's range function, except instead of returning a list of numbers, or in Python 3 an iterator of numbers, it returns an array with numbers running 0, 1, 2, 3, 4, 5, up to whatever you say here. Okay, so other ways to construct arrays, you can use linspace, which should be familiar to those of you using MATLAB. So you can say, construct numbers for me between 0 and 1, give me 5 numbers. Or you can use logspace, so that does the same thing, but it spaces the numbers logarithmically. So from 10 to the power of 1 to 10 to the power of 4, 4 different numbers, please. And if you want to include the endpoint, you can tell NumPy endpoint equals true. How did I know that the parameter there was endpoint? Well, if you type Shift-Tab in the notebook, so hold the Shift key, press Tab, then you get the signature for the function, and you can see, oh, it takes an endpoint parameter. And it takes a return step and a data type. So you can also modify those things if you want to. If you keep hammering Shift-Tab, the help will keep expanding and get bigger and bigger until it tells you everything. So there you go. There's the full doc string. So all of the NumPy functions are very well documented, and if they're not, you can file a bug report. They tell you, they've got a one-line summary of what the function does, a paragraph telling you sort of a little bit more detail, and then the input parameters, the returns, and often a few examples as well. So if I scroll down, yeah, there are a few examples and even other functions that you may be interested in. Another useful thing to be able to do is generate random numbers. There are various ways to do that in NumPy. I think this is the better style. So you start off by saying NumPy, inside your random module, grab the random state and initialize it with 0. So that's basically your seed. You can type any number in there you want, but that basically determines where the number generator will start generating numbers. So this thing doesn't really generate random numbers. There's no, well, that's another philosophical question whether random numbers exist or whether we can generate them, but NumPy just has an algorithm, and the algorithm starts at a point and it produces numbers that seem like they're random. So you tell it where to start. Why is it useful to be able to initialize every time? Well, if you do your experiment 100 times, you may want to verify that the results come out the same each time. So we often prefer to initialize the random numbers. Okay, so we construct our random number generator like this, and then it's got various methods on it. So you can do it's got a normal distribution, or it's got a uniform distribution. Shift tab tells me that the uniform distribution has got a low parameter and a high parameter and a size. So there I get 50 random numbers uniformly distributed.
If you start with the same seed, will you always get the same random numbers?
Yes. So there they are. I'm going to re-execute those two cells. See, they're the same every time. If I change the initial random state. But look what happens. I generate the random number generator, and now I'm going to keep executing only the current cell I'm on. See what happens? The numbers are changing. It's running further through that Mersenne twister or whatever they're using currently. All right, so that's uniform numbers. You can generate from a normal distribution. There are a whole bunch of them, and all you have to do is type RNG dot and the tab key, and you get a list of all these things. Chi-square, exponential, multinomial, Poisson, lots of different ones. All right. We saw a range already. Okay, so let's move on to array copies. So this is a place where a lot of people who have worked with MATLAB run into difficulties. NumPy is very careful about not wasting memory or about not reallocating memory unless you really need it. So imagine you load a massive image from your microscope or your telescope into your memory, and now you modify one pixel value or one color value. It would be terrible if you then had 2 copies of that image in memory, right? But this is what many of these systems do. So instead, what you expect is that you would load the array, and as you manipulate the array, it would stay in memory, and you would not make copies of that object. So in most cases, that's what you want, except it can be a little bit surprising sometimes. Like, look at the following situation. I've now created an array with numbers between 1 and 5. And then I called that array A, and then I assigned A to a variable called B. What is inside of A and what is inside of B? Okay, so they're both arrays with the same data, but are they the same arrays or not? They are the same arrays. So this is exactly the same as the rest of Python. When you do b equal to a, NumPy just points b in the direction of a and says that's the thing I'm looking at. So if you modify a, will you be modifying b? And if you modify b, you'll be modifying a. Yes. So what's that? It does. It does. No, it does. Like with dictionaries or with lists, you'll see that it's a yeah. So no, it does work that way with NumPy, with Python objects as well. Okay, so that's a good question. So how do you then copy an array when you actually need to? So let's look at this example quickly. So there I modified the third value of b, and when I print a, you can see that they both changed at the same time. Here then is the command to make a copy. So you can say c is a copy of a, and now when I modify c and a are different. Yes, sir?
I have a function and I have a parameter, so I pass a variable thinking that I'm passing a value, actual value, as a parameter to the function inside the function, and then it's modified. Will the local variables work with it? Does that affect the local variable as well, or is it?
So his question is, what happens if you pass, and tell me if I got this right, but he said if I pass a NumPy array as a parameter to a function, and that function modifies the array, does it also mean that the array is modified everywhere outside of that function? Is that correct?
That's correct.
Yeah. So yes, it does, because remember from our very first slide, all that NumPy knows is, hey, I've got an array, I've got a pointer to some data in memory, and I've got some metadata telling me how to interpret that data. So if you go and you modify that data in memory, it's modified, and all the different arrays that point to that data in memory will be modified too.
So that behavior is specific for NumPy, that wouldn't happen. Would that happen on these just regular variables in Python?
It would also happen for Python lists, for example, Python dictionaries. If you pass those objects into a function and you modify them, they're also modified outside. There's only one object in existence, and when that object gets passed into functions, you can modify those as well. So you have to make explicit copies if you don't want that to happen.
Are scalars done the same way?
Scalars are a little bit special in Python, so integers don't behave that way. It's mostly containers of any sort that works that way. So I'll do a 1-minute demo so that you can see what I mean. So here we see a new command. It's called reshape. So we'll start off with the numbers 0 to 11. And then I'm going to call a reshape on it. So reshape says take all those numbers and pack them into an array with a different size. What will that size be? Well, as long as the size adds up to 12 numbers, we're fine. So it can be 4 by 3, 3 by 4, 6 by 2, 1 by 12, 12 by 1. Anything else is fine. And if I do that, okay, there my numbers get repacked nicely into an array, 2D array. Now let's call that function, modify my array on Z. And what do you think will the first element be? Well, I think I gave it away. It will be 10. Oh, what happened there? Why is the whole first row initialized to 10? Well, this syntax over here means take the first row of the array. If I only wanted the very first element, I would have had to say x00. There we go.
So that's a list of lists. It's an array basically. The outer list is a list, and every element is a list.
Yeah, so NumPy arrays behave a little bit like lists of lists, but it's an n-dimensional array container, so it just means that if you have a 9-dimensional array, then it's an array that consists of a bunch of 8-dimensional objects that consist in turn of a bunch of 7-dimensional objects.
My instinct would have been that you have x, then in the brackets you would have a 0, and then you have another bracket that has another 0.
Yeah, like this.
Like that.
Yeah, but this is, you can do that, but this is the more efficient syntax. Yep. Okay, this one's important. So how do I don't think we've constructed this array yet. Let's, okay, so there's a new array called uni. What will the result be that I will store here in mask? Well, I'm asking, where is uni greater than 0? And it gives me back a Boolean array. So that's an array that tells you true or false depending on the condition you specified. So in this case, since I asked for all the positions where, all the whether uni is greater than 0, I got false most of the time, and then true in the 2 cases where it was greater than 0. These Boolean arrays can be used to index into another array. So you can do something like this. You can say uni where the mask is true, and then you get 5 and 5 out. Let's make it 5 and 6 just to make it clearer what's happening. Okay, so that basically takes that Boolean array, puts it on top of your array, and then only picks out the numbers where the corresponding elements are true. So you could also have written that as give me uni where uni is greater than 5. Done. Oops, greater than 0. There we go. Okay, take 5 more minutes. So, like we said, NumPy can go higher than 1 or 2 dimensional, so you can construct higher dimensional arrays. Let's call that P. There I have a 4-dimensional array, and the shape of that array is 3, 4, 5, 6. Okay, I think we can skip that for now. We looked at these properties already. Okay, last important thing. On NumPy arrays, you can perform operations like calculating the mean or the sum or whatever you have. So let's again start with this example. Let's call that big P. Okay, so let's see if I can calculate the sum of P. Well, there it is, it's 66. But that sums all the elements together. Often we want to sum across the columns, or we want to sum across the rows. How do you do that? Well, you just tell NumPy, I'm interested in axis 0, which is down, that's the rows, or axis 1, which is column. So, oops. There we go. So if you sum downward, then for each column, you get a single number that's a sum of that column. Yeah? You could probably make that P0. That's a little bit less readable, but it works. If I do P axis equal 1, how many numbers do you expect to see in the output? 3. What do you expect to see when I do P axis equals minus 1? Well, that's sort of the magic code name for sum the whole thing for me. Oh, no, that's the last axis. Sorry, maybe 0. Ignore all of that. Just use 0 or 1. And I think you can specify 2 as well if you want. There we go. So that means first sum across axis 0 and then sum across axis 1. But this is the one you're going to use most of the time. So you've got, in the same way, you've got mean, and you've got things like cumulative sum. Lots of different methods that you can apply. In fact, at the bottom of this, this notebook, if you scroll down a bit, you'll find, I'm going to make that small so it can fit onto the screen. Oh, not small enough to fit in. Oh, there we go. So that should keep you busy for a little while. I know how busy it keeps you because I spent a whole summer documenting all of these. So, all right. Okay, so yeah, go ahead.
Does NumPy distinguish between row vectors and column vectors?
Okay, she asked, is there a way to distinguish between row and column vectors? So I don't want to go too deeply into this because NumPy works a little bit different from most other tools you might have seen, but vectors in NumPy are one-dimensional, so they don't have a row or a column dimension. So if you do something like np.array 1, 2, 3, and you ask for the shape of that thing, it's just 3. Once you add a 1 to that shape, so if you make it if I add another bracket there, it becomes explicitly a row vector. So then it's 1 row, 3 columns. Or I could have done it the other way. I could have, well, I can call .t. That takes the transpose of your array. And then I get, what's that thing shape? That's a column vector, so that's 3 and 1. But you'll often end up running into these things that are only shape 3, and they're not either row or column vector. Okay. What's that? Yeah, so Chris is going to talk about matplotlib. So let me take one more minute. Last thing I want to mention is broadcasting. I'm not going to go into any detail about that, but I do want to warn you that, so in NumPy, when you combine 2 arrays of different shapes, in most languages that would give you an error, but NumPy has got a well-defined scheme for figuring out what the result of that should be. So in this case, it's obvious, right? You're taking the green vector and you're adding a scalar to it. It's obvious that it should just make that 3 spread across the vector and add them up. It's not so obvious when you get to higher dimensions, but it turns out that NumPy knows how to add those things together. So if you start off with an array like this, and you add a column vector to it, then NumPy will spread the column vector like that into a matrix and add them together. Same if you take a matrix and you add a row to it, it will spread the rows out and add them together. So just be aware of that. I've got a lot more detail on that if you're interested. It's called broadcasting. Yeah, so in this case, it's if you explicitly have a matrix that's, in that case, 6 by 1, that is the equivalent of a column vector. Or in this case, I've got a matrix of shape 1 by 1, 2, 3, 4, 5. So that's your row vector.
If you feed it a vector that matches the vector that you're feeding it, either has to be 1 or it has to match one of the
Exactly.
dimensions of the thing you're adding it to or multiplying.
Yeah, so if you give it an array like this and that shape matches that shape, then the machinery will figure out the rest.
Give it a longer one, like in the second example, if you give it a long one, it will automatically assume it's supposed to be right.
No, it doesn't make automatic assumptions. You have to give them the right shapes, and if the shapes align, then the addition will happen. I'm happy to talk more about this afterwards. I just want to give Chris a chance to teach you about matplotlib. So yeah, please grab me after the class. I'm happy to talk about anything we discussed here in more detail.